This is Daniel Coosberry, and in this lesson we're going to talk about the irrational numbers. First off, let's talk about what rational numbers are, and then maybe we can think of what irrational numbers mean. So rational numbers are the set of all numbers that can be represented as a divided by b, or a over b, where a and b are integers. So in this case, you can think of rational numbers as being fractions. Here's some examples where they can be represented as 3 over 5, it's an integer over an integer, or here's negative 12 over 13, integer over integer. Here's 7, it's also a rational number. You could think of that as maybe 7 divided by 1, or 0. You can also think about it as being rational. So rational is any sort of fraction that involves some integer divided by another. Rational numbers also have decimal representations that could look in one of two ways. So we could think about it as a terminating decimal, where we would write that fraction as a decimal, and at some point the numbers would stop. So we could, some sort of rational number ends up being like 2.2538 and nothing else. There's nothing back here. We call that a terminating decimal. Whereas we also have a repeating decimal. So we can, some rational numbers can be written as repeating decimals, where the numbers after the decimal repeat. Like this is 29292929, and then the dot 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 means that's going to happen until the end of time. We could also write that as 0.29 with the bar over it. That indicates that we're dealing with a rational number. So rational numbers can be written as decimals either by having a string of digits that at some point stop, or by having repeating digits, or we can write with a little bar over it. Either one of those are rational numbers. So that being said, irrational numbers are numbers whose decimal representation are neither terminating nor repeating. So there's not a fixed number of digits after the decimal. It doesn't stop. Also, they don't repeat. So here's some examples. We can think of the square root of 2 is irrational because if you write the decimal representation, it looks like this. And if you look at like the next 20 numbers, there's no sort of pattern there. Nothing repeats. Probably the most famous irrational number is pi, which is 3.14 and all this stuff. And as long as those decimals go, there's no sort of pattern or repetition that shows up. So we would call those irrational numbers. That means we can't write them as being, an integer over another integer, which makes them not rational or irrational. So since we're dealing with irrational numbers, we're going to end up talking about square roots, like square root of 2, square root of 3. They're all irrational. Square roots come into play when thinking about perfect squares. And a perfect square is a number that we get from taking an integer and multiplying it by itself and just squaring it. So if we take 1 and multiply by itself, we get 1. Take 2 and multiply by itself, we get 4, and so on. And so we have this pattern of 8 times 8 is 64, 9 times 9 is 81. All these bold numbers on the left are perfect squares because they come from taking an integer and squaring it. So what we get square roots from these by kind of going the opposite way. For example, let me take this one right here. If we get 3 and we square it to get the perfect square 9, we can go maybe the other way by, instead of squaring 9, we take the square root of 9, which is going to give us that original number 3 that we multiplied by itself. So square rooting is essentially the opposite of squaring. If we square 3 to get 9, we square root 9 to get 3. In the same way, we can go over here and say, oh, look, 15 squared is 225, so the square root of 225 is 15. Just kind of undoes the square, if you will. Now, not every single number is a perfect square. So like if we took the square root of 225, we would perfectly get 15, but there's so many numbers where you can't just write out a number, like a whole number, as the square root. So we saw like the square root of 2 was equal to 1.41, and then a lot of other digits after that. And it gets kind of messy, but one thing we can do with the square roots of things that aren't perfect squares is we can maybe simplify the roots a little bit to come up with something nicer looking. So this little yellow box shows you the product rule for square roots, and that's going to help us simplify square roots. So what this says is if you think of a and b as two different numbers that in this case you're multiplying together, the square root of two numbers multiplied together is equal to the square root of one number times the square root of another. So if you can think about breaking down a number into two factors, a times b, you can separate the square roots by doing the square root of one factor times the square root of another. And this is actually going to prove to be somewhat useful when we simplify roots, and I'll show you what I mean in example 1. Let's take the square root of 12 And let's start by maybe thinking of 12 as one number times another number. So maybe we can split that root up to the square root times the square root. So we can factor 12 into, in this case, let's do 3 times 4. This is 3 times 4. We're just breaking it down to factors. And then let's break this square root up into the square root of one factor times the square root of another. So what I mean is let's do the square root of 3 times the square root of 4 and just break it up like that. So when we do that, the square root of 3 is irrational. It ends up being like 1.7 something. If you stick that in your calculator, you end up some long decimal that doesn't repeat. So we'll just leave this the same way it is. But 4 is a perfect square. 2 times 2 gives you 4, which means the square root of 4 is 2. So we can actually write this as the square root of 3 times just the number 2, which the conventional way of writing this is 2 times the square root of 3. So this is how we would simplify square root of 12 in A, is we broke it up, we found a perfect square, and then we wrote the square root of that, and then we just got to kind of put the 2 in front because that's just typically how you would write it. So let's see if we can do that again. So with B, I have the square root of 250, which is not a perfect square. So I want to do kind of like what I did in A and see if I can break up 250 into 2 factors, and then maybe break those up a little bit more. So what happened in 12 was I split up 12 into 3 times 4, and 4 was a perfect square. It ended up coming out. So maybe there's a factor of 250 here that's also a perfect square. I see 25 in there, which makes me think, oh, well, 25 might be a perfect a factor of this, because 25 is perfect square. It's 5 times 5. So 25 times, I think, 10 gives me 250. So I can break that up into those 2 factors. And that's going to end up being really nice, because now I can take that square root and break it up into 2 square roots like I did up here. That's going to be the square root of 25 times the square root of 10. And since 25 is a perfect square, I can simplify this square root to be 5. Square root of 25 is 5. Square root of 10, it's irrational, and I don't think I can simplify it anymore, so I'm just going to leave it like that. 5 times the square root of 10. And that's how we would simplify 250. Now over here in C, we already have a number out here, but we can still simplify this radical number here. So let's do that the same way we did A and B. Let's we can leave the 3 on the outside, but let's think, is there any way of factoring 52 so that one of the factors is a perfect square? The only thing I can think of is maybe it's divisible by 4 somehow. So 4 times something would give us 52. So if you do the division to find out the other factor, 52 divided by 4 gives you 13. 4 times 13 gives you 52. Well, how do you know that? I sort of guessed that maybe 4 is a perfect square. That's a factor of 52. Just happened to work out. So in any of these, when you're asked to simplify, look for factors that are square roots, and that's really the only way it's going to get nice. So here we have the 4, and now we can break up the radicals. So this 3 is just going to live on the outside. It's going to be times the square root of 4 times the square root of 13. Okay, the only thing I can simplify here is the square root of 4 is 2, so I can do 3 times 2 times the square root of 13. And I would be done, except on the outside I have 3 times 2, which I know what that is. That's 6. So 6 times the square root of 13 is how this would be most simply written. So there was a factor of 4 in here that I pulled out, came out as a 2, and I multiplied that 2 times 3 to get 6 times the square root of 13. We can use this product rule also to multiply square roots, and it doesn't turn out to be too bad. In the same way you can break up 2 factors into 2 different square roots, we can also take the 2 different square roots and multiply them together, and simply by multiplying the numbers inside. So this one actually turns out to be a little bit more simple than what we just did. You have square root of 7 times the square root of 6, which according to the product rule up there, I can actually write this as the square root of 7 times 6. So that's nice. And that is the square root of 42. And that's about as simple as that one can get. So that didn't turn out to be too bad at all. Multiplying is not not terrible. I can do the same thing in b to the square root of 12 times the square root of 2. I can write that as the square root of 12 times 2, which would give me the square root of 24. And I would be done, except I know something about 24. I know that there's a factor of 24 that's a perfect square. That is, I can divide 24 by 4 and get a whole number. Let me tell you what I mean. So if I can break down 24, I'm sorry, didn't mean to write that. I can break down 24 into 4 times 6. Those are just two numbers that multiply to give you 24. And 4 is a perfect square, just like we did on the last examples. We can pull those perfect squares out to simplify this radical sum. So if I do that, I'll write this as 4 times 6, square root of 4 times square root of 6. Square root of 4 is 2, and the square root of 6 stays the same. So actually, when I do this multiplication, I end up with the square root of 24. But I should notice, wait, 4 is a factor of that number. I should pull that square root out as a 2, and then this is what's left over. And that's as simple as that gets. So there's a couple things to do here. But ultimately, the multiplication isn't quite as bad as simplifying radicals. So that's nice, I guess. The quotient rule for square roots is pretty similar. It simply says the square root of one number divided by the square root of another number is the square root of those two numbers, 1 divided by. So this means that I can take this problem that has a square root over a square root, and I can write it as one big square root of 54 divided by 6. I can just stick both those numbers inside and the division inside, which means I can simplify the inside of this now, because 54 divided by 6 is just 9. And that's just going to stay inside the square root. So see what I did? I used this quotient trick, and I wrote it as one big square root of 54 over 6, got the square root of 9. And then 9 is a perfect square, because 3 times 3 is 9. So the square root of 9 is 3. So this whole expression here, which is not obviously 3, turns out it's 3 using this quotient rule. Got a perfect square. We got 3. Okay, so we can do the same thing with b. We got the square root of 90 over the square root of 2, which I can write that as the square root of 90 divided by 2. Then do the division. So all this is in the square root. 90 divided by 2 is 45. And then I should probably try to simplify that a little bit if I can, since that's a pretty big number. So let's see, is there any factor of 45 that's a perfect square? I think there is. Maybe. Let's see. Yeah, so 9 times 6, nope, not 6. 9 times 5 gives us 45. So we can simplify this the way we've been doing. We can break up this radical into square root of 9 times the square root of 5. Square root of 9 is a perfect square. That's 3 times the square root of 5. So this one's a little more involved, but once we put this as the square root of 90 over 2, we can start working on this like some of the previous problems and get this simpler looking answer. Adding and subtracting square roots is a little different because we can't simply add numbers inside and outside. We can't break up the square root or stick it together like we can when we multiply and divide. So this little blurb here is telling you what you can't do. You can't just take, for example, the square root of 4 plus 5 and say that's equal to the square root of 4 plus the square root of 5, because it's not. If you put both those expressions in the calculator, you'll find they're not the same thing. However, when we're adding, we can do something to simplify expressions, and it's kind of written here. These are things you can do. I don't know if this is algebraically a really nice thing to read, but I'll demonstrate an example for. Here what we have going on is we're adding two different radicals, and they both have this square root of 3. And the way to make this simpler is you can think of the square root of 3 as a thing. So maybe in the same way we'd think about a variable x or variable y or like x squared. Think of it like something, and this is saying, well, 7 of these things plus 6 of these things is really giving us 13 of these things. We can think about the square root of 3 is just kind of something that we're adding multiple versions of. So there's 7 square root of 3s plus 6 more square root of 3s would give us 13 square root of 3s, and that's kind of how we can do addition with radicals. It's not, again, this doesn't work, but this is kind of what this is saying is if you have some sort of square root of c and then some more square root of c's, you can add those coefficients on the outside, the 7 plus 6, in order to get something simpler. So that's what we did with the 7 plus 6, and we got the 13. So that works in some less obvious problems. Let me move this over. Some less obvious problems where we have the square root of 3 and the square root of 27. We can actually simplify this in a way because we know how to simplify the square root of larger numbers. For example, I know that there's a 9 in there. If I were to write this as the square root of 9 times 3, 27 is 9 times 3, I can pull that square root of 9 out since it's a perfect square. So I'm just doing this how I would do all those other examples, simplifying it a little bit. And I get the square root of 3 plus square root of 9 is 3 times the square root of 3. So I've simplified the square root of 27 now to where now I have a square root of 3 here and a square root of 3 here. So I can think of this as 1 square root of 3 plus 3 more square roots of 3 is 4 square root of 3. What we're doing is really combining like terms. You know, if this is an x and that's an x, 1x plus 3 more x's is 4x. So that's kind of how this is working. And it wasn't obviously what we needed to do here, but when you see square root of 27 or square root of a larger number, you can probably simplify that. You can probably pull out a perfect square like we did here and have that. So that's how you would want to tackle a problem like this. And so when you see something like C is probably really messy, is we've got some big numbers and there's really nothing we can do unless we find, like in the previous problems, we find some sort of common square root. So here we had a common square root of 3. We had a common square root of 3 here and square root of 3 here. So let's see if we can simplify these numbers so that we see some sort of common thing. I know the square root of 63, well, 63 can be broken up as a factor of 9 in it. 9 times 7 gives me 63. And I'll just leave that there for a second. And then I also know there's a perfect square in 28. 28 is divisible by 4. 28 is equal to 4 times 7. So I've got a few perfect squares in there. So now if I break up those radicals, like I've been doing this whole time, this is the square root of 9 times the square root of 7. This is the square root of 4 times the square root of 7. So now I've broken those up using the product rule. Well, now I can take these square roots. Square root of 9 is 3. That doesn't do anything. And then the square root of 4 is 2. And that kind of stays there. Now it's a little more evident what my last move should do. So I have a square root of 7 that popped out here, square root of 7 that popped out here. I didn't know that was going to happen when I started this. But when I pulled out the perfect squares, those 7s popped up. So now I can simplify this just like I did A and B. And I say, okay, well, if I have 3 square root of 7s and I take away 2 of them, all I have left is 1 square root of 7, which you can leave out the 1. You can just say that's square root of 7. The last thing in this section is what's called rationalizing. And rationalizing is a process that ensures that when we report our final answer, when we're talking about radicals, that we don't have any sort of radicals or square roots or anything in the denominator. So for example, in letter A, we have a square root of 5 in the denominator, and it's just kind of convenient to not have that. And so there's a way to get around that, and it's not a terrible thing to do. What we're going to end up doing to get that square root of 5 out is, what if we took that square root of 5 and we multiplied it by another square root of 5? So the idea here is if you were to do this, we're doing square root of 5 times the square root of 5. This is actually amounts to doing the square root of 5 squared. And by doing that, you actually end up taking that square root away. So if you take the square root of 5 and you square it, that square root just drops off and you end up with the number 5. So taking a square root of some number and multiplying it by the square root of that same number makes that whole square root thing go away, and it gives you a nice not square root number, a nice not radical. And if we could do that in A, then it would get that square root out of the denominator. So in order to do that, we're going to multiply this number by the square root of 5 in the denominator, and we're going to have to also multiply it by the square root of 5 in the numerator, and that's going to ensure that that we haven't actually changed the number. We're just multiplying it by something dividing by itself. So that's something over itself. It always gives you 1. Doesn't actually change the number. And when we do that, we end up with 5 in the denominator, because that's what happened. We kind of scribbled that over here. And in the numerator, we end up with 30 times the square root of 5, which is a pretty nice way of writing that. And even though our answer looks messier, we have now rationalized because we have an answer that does not have a square root in the denominator. So we've done good work here. So we can do the same thing with b. We got the square root of 5 over 7, which may look okay, but if we use our quotient rule, what this is saying is this is actually the number square root of 5 over the square root of 7, in which case it has a square root in the denominator. And so we would want to rationalize that number to get it out. So to do that, let's do the same little trick we did in letter A. We will multiply the square root of 7 times itself, and that'll make that square root go away. But then we'll also have to multiply the numerator times the square root of 7, just to make sure we haven't actually changed the number. We're multiplying by something over itself, which is really just 1. We haven't changed anything. So when we do that, our denominator becomes 7, and our numerator becomes the square root of 5 times the square root of 7, which we can use our product rule then to call that the square root of 35 divided by 7. And that's about as simple as that one gets. So rationalizing is something you got to look out for when you're working with radicals, because at the end of the day, if you have a square root in the denominator, it's just not considered an appropriate way of reporting that answer. So, but the nice thing is this method works pretty much the same every time. You just multiply this denominator by itself, square root goes away. We do that same thing over here, and that's it.